Welcome back to the deep dive. Our mission today is pretty laser-focused. You've asked us for a high-yield, comprehensive summary of general chemistry foundations.
That's right.
We're talking stoichiometry, kinetics, equilibrium, basically all the way through electrochemistry. And this isn't just, a simple refresher.
No, not at all.
This is about distilling the core principles you really need, especially if you're heading into advanced science, medicine, that kind of thing.
Exactly. We're not going to dwell on the basics you already have down. We're really going to focus on the conceptual traps, the subtle definitions, and the applications that connect these textbook ideas directly to biological systems.
So moving past just the what and into the why.
Precisely. We need to understand why these laws work the way they do.
Okay, let's unpack this. Let's start at the very beginning. The language of quantity. I'm looking at Chapter 4, Stoichiometry and Solutions.
Right.
The mole, 6.022 times 10 20 torta particles. We know it's our unit of convenience, like a dozen eggs. But let's jump right to a higher level concept. Normality.
Yes. Normality.
Why do we sometimes need to use normality or equivalents per liter instead of just good old molarity?
Well, because molarity can sometimes miss the point. It tells you how many molecules you have, but not necessarily how much reactive stuff is in there. Normality tells us how many reactive units or equivalents are present.
Reactive units like protons.
Protons are the classic example. Think about a polyprotic acid, like carbonic acid, text CO3O3. It's diprotic, meaning it can donate 2 hydrogen ions.
So one molecule has 2 shots to give, so to speak.
Exactly. So a 0.5 molar solution of carbonic acid is actually 1 normal. The normality instantly scales the concentration by the number of active protons it can donate. It gives you a much better picture of its acid neutralizing power.
Okay, so normality is critical when the particle of interest is something other than the whole molecule. Protons or maybe electrons in a redox reaction.
Precisely. Now let's tackle another one, a really critical distinction in concentration, molarity versus molality.
M versus M.
Right. Molarity moles of solute per liter of solution is our day-to-day workhorse. We use it for rate laws, equilibrium constants, pH, pretty much everything.
But there are specific cases where we absolutely must use molality moles of solute per kilogram of solvent.
And those cases are the colligative properties.
Boiling point elevation and freezing point depression. But why is the distinction so important there? Why can't we just use molarity?
It all comes down to temperature. Molarity is based on the volume of the solution and what happens to volume when you change the temperature.
It expands or contracts?
It changes. Subtly, but it changes. And if you're trying to measure a precise change in boiling or freezing point, you can't have your unit of concentration shifting under your feet.
I see. But the mass of the solvent doesn't change with temperature.
Never. A kilogram is a kilogram. So molality is temperature independent. That's the whole reason it's the gold standard for those specific calculations. It isolates the measurement from those little volumetric shifts.
That's a great takeaway. It brings us neatly into our next big theme, dynamic processes. We're moving from static amounts to the speed and the balance of reactions. Let's start with kinetics.
The speed of reactions.
What does collision theory tell us is absolutely required for a reaction to even happen?
2 things have to be perfect at the exact same moment. First, the molecules have to collide with the correct geometric orientation. They have to fit together like a key in a lock.
And second,
energy. The kinetic energy of the collision has to be greater than a certain minimum threshold. We call that the activation energy, or $. If either of those is missing, wrong angle, or not enough punch, the collision is useless. No reaction.
And the rate of the reaction depends on how often these effective collisions happen. Which brings us to rate laws, and this is, I think, a huge conceptual hurdle for students.
It really is, because the temptation is just to look at the balanced chemical equation and assume the stoichiometric coefficients are the reaction orders.
But they're almost never the same.
Almost never. The reaction order must be found experimentally. It has to be. Because it doesn't reflect the overall equation, it reflects the mechanisms, specifically the molecules that are actually involved in the rate-determining step.
The slow step.
The slowest step in the chain. That's your bottleneck. If the reaction is what we call an elementary single-step reaction, then yes, the coefficients match. But that's the exception, not the rule.
This is so important in biology. We sometimes see reactions described with pseudo-first-order kinetics. What's going on there?
That's a great question. In biological systems, you're usually in an aqueous environment. So if water is one of your reactants, it's there in such a massive excess that its concentration basically doesn't change during the reaction.
That's effectively a constant.
Right. So we just absorb that constant value into the rate constant. And mathematically, the reaction suddenly looks like it only depends on the other, less concentrated reactant. It simplifies a complex mechanism into a much more manageable first-order model.
And what about catalysts? In biology, we call them enzymes. We know they speed things up.
Yeah. They do it by lowering that activation energy, the ELR. They provide an alternate, a less energetically demanding pathway for the reaction to follow, a shortcut.
But they don't get used up in the process.
Correct. And this is the crucial part.
Yeah.
A catalyst speeds up the forward reaction and the reverse reaction equally. It helps the system get to equilibrium much, much faster.
But it doesn't change where that equilibrium lies.
Absolutely no effect. The final ratio of products to reactants at equilibrium, the constant TOS, remains completely unchanged.
That sets us up perfectly for equilibrium itself. The state of balance, we define it not as static, but as dynamic.
Exactly. It's not that the reactions have stopped. It's that the rate of the forward reaction now equals the rate of the reverse reaction. Microscopically, things are still happening like crazy. But macroscopically, the concentrations look stable.
And from an energy perspective,
that's the point of minimum Gibbs free energy. Delta G is 0. And it's the point of maximum entropy for that particular system. The system is as stable as it's going to get.
So, to predict which way a reaction will go to reach that stable point, we compare the reaction quotient, Q, to the equilibrium constant.
Right.
Q
is the goal. It's the perfect ratio of products to reactants at equilibrium. Q is just the ratio right now, at any given moment.
So if Q is smaller than Q,
it means you don't have enough products yet. The ratio is too small. So the reaction spontaneously shifts forward to make more products. Delta G is negative.
And if Q is bigger than Q?
You've overshot. Too many products. The reaction will spontaneously run in reverse to get back to that ideal ratio. Delta G is positive for the forward reaction. It's this constant drive to restore the balance.
And that's Le Chatelier's principle. How a system responds to stress.
Any stress. If you change the concentration or the pressure or the volume, the system will shift to counteract that change. It's trying to get the value of Q back to the fixed value of kappa.
You add more product, Q gets bigger. So the reaction shifts left to use up that extra product.
Exactly. But here is the single most important distinction we have to make. Concentration, pressure, volume, they all shift the position of the equilibrium, but they don't change the value of constant.
Okay, so what does?
Only one thing. Temperature. Temperature is the only stress that changes the numerical value of the equilibrium constant itself. That relationship is actually described by the Van Hoff equation, which links directly to the reaction's enthalpy.
To really get why equilibrium settles where it does, we have to dig into the energy, which takes us straight into thermochemistry and state functions.
Yes, state functions are, they're a beautiful simplification. They describe the state of a system like its pressure, temperature, enthalpy, entropy, and they don't care how the system got there.
Path independent.
Path independent. This is totally different from process functions like heat, Q, and work, W, which depend entirely on the specific path you take.
So if I'm tracking this, that means if we know the starting and ending points, we can calculate the change in enthalpy, or delta H door, without knowing every single intermediate step. That's Hess's law, isn't it?
That's the power of Hess's law. Because enthalpy is a state function, you can add up the energy changes of individual steps to get the total. It's why we can say that breaking a bond is always endothermic, it requires energy, and forming a bond is always exothermic.
Let's talk about entropy, delta SL. The simple definition is disorder, but that feels insufficient, especially in biology with its highly organized structures.
We have to move beyond disorder. It's not a very precise term. A better way to think about entropy is as a measure of energy dispersal. How spread out is the energy in a system? How many different microscopic arrangements are possible?
So it's not about messiness, it's about possibilities.
Exactly. The second law of thermodynamics says the entropy of the universe is always increasing. Energy is spontaneously spreading out, dispersing, unless something stops it.
And the final arbiter of whether a reaction will happen is Gibbs free energy, delta G Deller. The famous equation, delta HT delta del.
It's the ultimate judge. It combines the drive to lower energy, which is enthalpy, with the drive to disperse energy, which is entropy. If delta G is negative, the process is spontaneous. It will happen.
Okay, moving from energy to phases. The gas phase. We have the ideal gas law, PV nRT of Theo. It's built on a couple of big assumptions, right?
Two very big and very wrong assumptions. First, that the gas molecules themselves have zero volume, and second, that there are absolutely no intermolecular forces between them.
Which is useful for calculations, but obviously not true in the real world. So when does this ideal model break down?
It breaks down when you force the molecules to acknowledge each other's existence.
By pushing them closer together?
Precisely. Real gases deviate most from ideal behavior at high pressure, which shrinks the container volume and makes the particle volume suddenly matter, and at low temperature, where the molecules are moving so slowly that those little intermolecular attractions can finally take hold and make them stick together.
And this leads us to something incredibly relevant in medicine, Henry's law.
Yes. Henry's law connects the gas phase to the liquid phase. It simply states that the amount of gas you can dissolve in a liquid is directly proportional to the partial pressure of that gas sitting right above the liquid.
So more pressure above, more gas dissolved below.
Exactly. And that is the fundamental mechanism of gas exchange in your body. In your lungs, the high partial pressure of oxygen in the air you breathe in forces oxygen to dissolve into your blood.
And it explains dangerous situations too.
Oh, absolutely. Like decompression sickness, the bends. A diver deep underwater is breathing air at high pressure, so a lot of nitrogen dissolves in their blood. If they come up too fast, the pressure drops suddenly. The nitrogen is no longer soluble.
And it comes out of solution as bubbles in their tissues and joints.
Which is incredibly dangerous. It's a direct physical manifestation of Henry's law.
That's a perfect example.
Yeah.
Okay, let's pivot to our last major section. The movement of protons and electrons. Acids and bases first. There's a whole hierarchy of definitions here.
Yeah. There is. You should think of them as Russian nesting dolls. The biggest, most inclusive definition is the Lewis definition. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor.
This one doesn't even require protons.
Correct. It covers so much more chemistry. Inside that, you have Brunstad-Lowry, a proton donor and a proton acceptor. And then the smallest, most restrictive doll is Arrhenius, something that makes text plus RH or text RH in water. For advanced science, you really want to be thinking in Lewis terms.
And the strength of an acid is directly tied to its conjugate partner.
Inversely tied. A very strong acid, one that completely gives up its proton, leaves behind a very, very weak and stable conjugate base. It's happy on its own.
And that's why titrating a weak acid with a strong base gives you an equivalence point with a pH above 7.
Exactly, because when the weak acid is all used up, you've created a solution full of its conjugate base. And that conjugate base is not inert, it's a weak base itself. It reacts with water, pulls a proton off, and generates hydroxide ions, making the solution basic.
Which our bodies have to fight constantly. We rely on buffer systems.
We do. Buffers are just equilibrium systems in a bottle. A weak acid and its conjugate salt mixed together. They're designed to absorb any added strong acid or strong base with only a minimal change in pH.
And the most important one in us.
The bicarbonate buffer system in our blood plasma. Dextanetex, TXTO303, it's what keeps our blood pH in that incredibly narrow, life-sustaining range. And it works hand in hand with our lungs and kidneys.
All right. From protons to electrons. Redox reactions. AO the lion goes GER.
Loss of electrons is oxidation. Gain of electrons is reduction. And always remember, the oxidizing agent is the species that gets reduced, and the reducing agent is the one that gets oxidized.
To keep track of it all, we use oxidation numbers.
They're just our bookkeeping tool for electrons. We have the rules. Free elements are 0, group I metals are +1, oxygen is usually -2, unless it's cinder peroxide, then it's -1. You have to be able to follow the electrons.
Sometimes a single chemical species can play both roles at the same time. What's that called?
That's a special type of reaction called disproportionation. A single species is simultaneously oxidized and reduced.
Can you give us an example?
Chemically, the decomposition of hydrogen peroxide is a perfect one. The oxygen starts at a -1 oxidation state in text O2, and it ends up as -2 in water, which is a reduction, and 0 in oxygen gas, which is an oxidation.
And biologically?
Biologically, the enzyme superoxide dismutase is a lifesaver. It takes the very dangerous superoxide radical and catalyzes its disproportionation into harmless oxygen and hydrogen peroxide, a vital protective mechanism.
Then harnessing that electron flow for energy.
Huh.
That's electrochemistry. We have two main cell types.
The galvanic or voltaic cell and the electrolytic cell. A galvanic cell is spontaneous. The chemistry wants to happen, so it runs on its own, producing a voltage. Think of a battery that's powering something.
Delta G is negative.
Delta G data is negative, and the EMF or voltage is positive. An electrolytic cell is the opposite. It's a non-spontaneous reaction that you have to force to happen by pumping in energy. This is what you're doing when you recharge a battery. Delta G is positive.
The confusing part is always the charge on the electrodes.
It is. So don't memorize the charge, memorize the process. Oxidation always happens at the anode. Reduction always happens at the cathode. In the spontaneous galvanic cell, the anode is the source of electrons, so it's the negative terminal. But in the electrolytic cell, an external power source is involved, which forces the anode to be positive to attract anions for oxidation. The process is the same. The sign flips.
Bringing this back to biology one last time, the mitochondria acts like an electrochemical cell.
It acts very much like a specific type, a concentration cell. The whole point of the electron transport chain is to pump protons from the mitochondrial matrix into the intermembrane space.
Creating a huge concentration gradient.
A massive one. That gradient is a form of stored potential energy, what we call the proton motive force. The tendency for those protons to flow back down their gradient to equalize concentrations is what powers the synthesis of ATP. It is the perfect marriage of chemistry and life. So we've covered a huge amount of ground here. I think the main takeaway for you should be how interconnected all these ideas are. Kinetics influences equilibrium, which is driven by thermochemistry, and all of it shows up in the movement of protons and electrons in living things.
So what does this all mean?
It means you need to focus on the underlying principles. Don't just memorize, ask why. Why, Malady, there? What's the one thing that can actually change? When do our ideal models start to fail us? That's where the real understanding is.
It's the blueprint for everything that comes next. To really lock this in, let's leave you with a final analytical exercise based on that redox material we just covered. Okay, here's the reaction. Text SnCl2 plus text PbCl4 plus text PbCl2. Your task is to use your knowledge of oxidation numbers to identify the reducing agent and the oxidizing agent.
And a little hint. Assume chlorine keeps its usual -1 oxidation state throughout the reaction.
Think about which element is losing electrons and which one is gaining them. Keep applying these core concepts. They really are the key to unlocking the complexity of advanced science. We'll catch you on the next deep dive.